Hello and welcome back to the plasma physics course. Today we're going to pick up from where we left last time, and in particular we're going to talk a little bit more or a lot more about the Hamiltonian method. Of course, I hope no surprise, Hamiltonian method for working in plasma physics and study the behavior of a plasma physics system. If you remember, last time we just reviewed the Hamilton equations, which you're all familiar with. And we said we were going to look at a specific example that's in chapter 3.7.2 of our textbook, which we're going to follow pretty closely today. Hope you'll be happy. And what's in the chapter is the Hamiltonian treatment for an axially symmetric magnetic mirror field, which I'm going to type very slowly. I'm actually going to pause the recording and type because otherwise you'll get bored. Here we go. I'm done with my typing. We have the topic we're going to discuss, hopefully sufficiently well defined. And let's see now what the book, the textbook, tells us about it. The first step is to pick our frame of reference, the system of coordinates we want to use. And this comes up often in physics. In fact, it comes up anytime you want to describe a physical system, you have to define your coordinates. And you're well familiar with the fact that in a treatment like the Hamiltonian treatment, you don't necessarily need to use spatial coordinates. But that's what we're going to do today. And you've also learned in other places in physics that setting up your coordinates is very important in the solution of a problem. If you pick the wrong, in quotes, set of coordinates, you may make the problem more difficult mathematically than it needs to be. All that long introduction was to say we are going to use cylindrical coordinates because those are going to make our life easier. Now, if I could just spell cylindrical, here we go. Now, contrary to what the book does, I'm going to use the lowercase letter r, the angle phi, which I'm going to type the way I type phi, which is not the way it looks in the book, of course. And if you look at the textbook, you'll see that I've replaced the textbook variable rho, that's lowercase Greek letter rho. Sorry about that. With the Latin letter R, And the reason why I'm doing this is that if I use rho, I'm afraid it's going to become difficult to distinguish between rho and p, which are conjugate momenta, which we're going to need in the Hamiltonian description. And that will just make this more confusing than it needs to be. In conclusion, we are going to use R and not rho. Here we are. I pause for a moment to express my disappointment with the iPad that automatically capitalizes anything I want to be lowercase, but not words that are supposed to be spelled uppercase. Anyway, I also put everything in green so we're clear which arrow goes where and what all this means. Let's try to do something useful now. And the first thing I want to do is to write the Lagrangian for my system. Now, I find this interesting in fusion or plasma physics in general work, that it seems to me that a lot of the work actually gets hidden into knowing how to write the Lagrangian. In this case, I'm going to give you the Lagrangian, and you will forgive me, but I can't refrain from using a cursive letter for the Lagrangian. And the definition of the Lagrangian is 1/2 m, that is the kinetic energy, which I write as 1/2 of m times r dot square plus r dot phi dot square, sorry, r square phi dot square plus z dot square. And then I need the potential. And you may wonder where on earth this came from. I hope you've seen this in ENM or in some other course, but I'm going to use the vector potential A, and therefore I'm going to need A sub r dot plus A phi r phi dot, velocity in the phi direction, plus A z z dot. From here, you can calculate the conjugate momenta. I'll leave that as an exercise. It's also not spelled out in the textbook, but you know how to do this. I believe maybe not all of you actually have already passed the classical mechanics GDE, but you know how to calculate moment. So I'll just write the results. P sub r is going to be m r dot plus q a sub r. P phi is m r square phi dot square plus q times r times a phi, and p sub z is easier, is m z dot plus q a z, similar to the r piece. Let me play with colors again. where these are going to be the conjugate momenta. There. Okay. A moment to make this green. Here we go. And from here, we can proceed to specialize our system to the system we're interested in, or we can do that after writing the Hamiltonian, which is the way our textbook proceeds. And I feel that that's get more a better way, let me say, to proceed, because by doing so, I'm going to have the Hamiltonian for the general case, and then I'm going to specialize it to the case we're going to look at. If I wanted to do something different, I will have the Hamiltonian ready. Okay. The Hamiltonian then follows, and for the sake of not spending too much time doing the type of calculation you're very familiar with, I'm not going to do derivation. Please do it once in your life as an exercise. Maybe I'll give it to you as a problem in the next homework problem, so that you're. I'm sure that you write it at least once, even if you don't do it yourself. All right, the Hamiltonian, 1/2m p sub r minus q a sub r square plus p sub phi minus q r a phi square divided by 2m r square plus 1/2m. Oh, that's horrible. It's my destiny never to manage to write anything straight. All right, let's do it this way. Sorry about that. 1 minus 2m p sub z minus q a sub z square. You know this, but let me remind you, when you write the Hamiltonian needs to be expressed in terms of q's and p's, not q's and q dots, where q and p are generalized coordinates and conjugate momentum. We do occasionally see in classical mechanics exams people answer the question, what is the Hamiltonian of the system, with an expression that contains quantities like x and vx. That's the wrong set of coordinates. That's not the Hamiltonian. It's an intermediate step. Okay. This is what we're going to use, and we're going to make the restrictive assumption that's going to be good enough for our calculation that the magnetic field is has axial symmetry. I've already said we would use axial symmetry. It's all spelled out clearly up here in case you missed it. And I'm going to make one more assumption. I'm going to assume that b phi is equal to 0. Now, that is not a necessary assumption, but it's going to simplify my life. I could carry the rest of the calculation, including b phi. It's just more work. And what really matters is contained in what we're going to do, even with b phi equal to 0. The advantage, the reason why we do that is that we can greatly simplify the expression for our vector potential, and therefore of our Hamiltonian, as we'll see in a moment. All I have left is a phi of r and z in the phi direction. And a sub r is equal to a sub z is equal to 0. Then I can calculate my magnetic field as the curl of my vector potential. And if I do that, I find the following expression: BR is minus d a phi dz, and bz is 1 over r. Oh, sorry, I made a big r. I'll tell you why in a moment. That was an accident, but for a reason. D over dr r a phi. Now, I've not cheated or anything up to here, but if some of you are familiar with the axisymmetric assumption for tokamak work, which is a pretty good assumption. When we describe tokamaks, we typically assume axis symmetry, as we're doing now. Then we find that the poloidal field can be written in a way that's pretty similar to this. So let me emphasize that connection, which is going to have some small risk of making things actually more confusing, but in tokamaks, I can calculate the poloidal field in this way. BR, major R, I think I should make a plot of the geometry. So let me do that in a moment. Is going to be equal to 1 over R, sorry, minus 1 over R d psi d z. Bz is equal to 1 over R d psi dr. Okay. What is all this stuff now is the point I want to clarify. So here's my tokamak. It doesn't need to have circular cross section. What matters to me is that here I have my axis of symmetry. This is the z direction. This is the angle phi. That's the ignorable coordinate. And here is the r direction. And in the plane phi constant, the two components of the field that are playing on that plane are BR and BZ, and I can calculate them this way. Now you see how this expression relates to the expression above. There is clearly a correspondence between what we're calling psi in tokamaks and what we found was RA phi in our mirror system. For the expression for BR, I've just multiplied and divided by R to obtain the one I had. I've multiplied and divided by R the expression I have above to obtain the one I have below. And the quantity psi is what is called the colloidal flux. Where flux stands for magnetic flux. Okay, then the work we're doing here, the expressions we're looking at, are going to look very familiar to somebody that's already worked on tokamaks and maybe using fluid models or whatever, and doesn't know anything about the Hamiltonian method. That this may may or may not help any of you. The catch I was hinting at above is that this is the end of the intermission. We are going to keep following our textbook, and unfortunately, our textbook is going to use the symbol psi for something different. But let's get back to our problem, take our steps following the textbook. We had this expression for the conjugate momentum. Let me call this equation. No, not there. Thank you. 1 okay, better. And I'm going to take that expression that you've just seen and set to 0 AZ and AR and obtain the simplified now expressions for my conjugate momenta. In particular, P sub R is just going to be equal to M R dot. not that scribbled there, but P, sorry about that, sub phi, well, that doesn't change because A phi is not 0, so that's going to be still M R square phi dot plus Q R A phi. Sorry about that. And PZ is going to be equal to MZ dot. Moreover, P phi let me type this rather, is going to be, oops, a constant. Here we go again. There. Made it happen again. It's always fun. Okay. We know that P phi is a constant, and we're going to use this in a little bit. We're also going to assume that the magnetic field is time independent. Then, because of the way we have set up our coordinates, they don't depend on velocities, there is nothing else that could break that conservation. The Hamiltonian is going to be equal to the total energy, and is also going to be a constant of the motion. Let me type that. No, wrong one. Sorry. Notice that I've also assumed that there is no electric field. That wasn't in the Lagrangian when we got started. The Hamiltonian is going to be a constant, which is also going to be equal to the energy. And that constant, now I'm going to write the expression. If you go back up here to our expression from before, that I will now call 2, you set A sub r equal to 0. You set A sub z equal to 0. You set P phi with its expression to be a constant. And you end up with P sub r over square, sorry, over 2m plus P sub z square over 2m plus, here is the catch, psi of r and z, and is all equal to w. where with W I mean energy. The catch is that psi is now going to be in this description an effective potential. And not what I called the magnetic flux earlier. Unfortunately, there is a finite number of letters, especially Greek letters. And for that reason, we end up using the same letter for different things, and I know that that can be confusing. The definition of psi, which you can get from above, is easy to write. It's 1/2 mr² times p phi minus QRA phi square, where I'll remind you that p phi is also a constant. Okay, then see if I can find the correct color, probably not. So I'll just make an approximation. That should be good enough here. Let's see, that is horrible. Let me work on it for a moment. Well, on second thought, that's not really worth our time. I just learned that the default colors have changed somehow, or I picked a strange color by accident when I defined my color pens. So we'll have to deal with two colors that are completely different. I should have just left it black. Okay, let's not waste time discussing colors. The first thing that we can see from the expression of the Hamiltonian, maybe I can frame that. And the expression for psi as well. The first thing we see from the Hamiltonian, I was saying, is that given a particle energy, W, comes from the initial conditions, the motion of the particle is going to be limited or bounded by the surface W equal psi. Because if psi was larger than W, I would need the other two terms in my Hamiltonian to be less than 0, but they're both positive definite. And therefore, I can't move out of that region. So this is, in fact, a type of motion that you're most likely pretty familiar with. It's a motion of, it's a two-dimensional motion of a particle in some type of effective potential, which is also two-dimensional. That means the whole motion is two-dimensional. Okay. Now, one additional thing that we observe is that since p phi itself is also a constant, then we can define the shape of psi, and we do see that psi is positive definite as well. That means that for my problem, I can assign initial conditions, and my initial condition psi is going to be positive, or at the minimum, it's going to be 0. And that occurs when, okay, this is not hard work. If p phi is equal to q r a phi, then psi is equal to 0. For any other value of p phi and r and a phi, psi is going to be positive. Then if I plot now psi versus r, I can see that it's going to be 0 at some special value of r, and it's going to be larger than 0 elsewhere. It may come back down to 0 more than once, depending on what a phi looks like, since a phi in general is also a function of r and z. But in particular, around this point, if a phi doesn't change very quickly, this is going to look like a quadratic potential well, and then it's going to go wherever it's going to go. We'll do something like this, for instance. I'm trying to reproduce more or less what we have in the book. I will just put the book figure on my screen, but since I'm going to put this on YouTube, it's not. I don't want to violate any copyright. I'm just going to refer you to the book. This is going to be figure 3.35. One additional piece that's emphasized in this figure is that if I now fix the value of W, I'm going to have some bounds for the motion in the r direction. It's the classic problem of potential well. Let me do here a couple of arrows to emphasize where those bounds are. One is here, and the other one is there, where psi is equal to W. I did say it, but I did not write it. So that's the energy of my particle. Okay, then. We've found that my motion is bound in the R direction. And as always, I'm taking a lot longer than I expected. But let's try to get to the end of this, maybe moving a little more quickly. I hope this is helping and this is all making sense. Now, in the interest of time, I'm going to pause my recording again, make an attempt at reproducing the next picture in the textbook, and then we'll discuss it quickly, try to get to a couple more things today. Okay, finally, here we are again. Here is my wonderful rendition of figure 336 in the book, where I'm showing the direction of magnetic field lines in the RZ plane, and I have those other two curves around it that I will describe in a second. And the way we are going to proceed is to calculate the magnetic flux through a surface of that's the radius r that's perpendicular to the z axis. So here is what I want to calculate. This is something you're familiar with. And here I'm going to use this phi as defined as the integral between 0 and some r. I could call it r some symbol, r hat, or number, doesn't really matter. Bz times the surface 2 pi r in the r. But you do remember what was the expression that we had for Bz, not this one here. The 1 over lowercase r derivative with respect to r of r a phi. And that's what I'm going to replace in my expression down here now. Let's see. Okay, then let's see what we get. We get the integral from 0 to r of the expression for Bz that we just looked at, 1 over r d over dr of r a phi. And let me put it in brackets so that I can emphasize that this is the expression for Bz, and everything multiplies still 2 pi r dr. Now, this is a really difficult integral that gives us immediately that phi is equal to 2 pi r k phi. Again, if you're familiar with what we do with tokamaks, and you remember what I said a few minutes ago, the quantity Ra phi is called psi in tokamaks, and it's the poloidal magnetic flux. Well, here it is. This is, in fact, really magnetic flux up to a factor of 2 pi. But what we notice from here is that since Q is a constant, I can multiply this by Q. And the quantity Q times phi or QR a phi identifies a flux tube. That's a magnetic field line, essentially. In other words, where this quantity is a constant, or rather the minimum of the potential is on a constant value of Q R a phi, that is, it follows a magnetic field line. Now, if my particle starts with an energy that is above the minimum of psi that I had here, exactly as in the sketch I have to reproduce figure 335, then it's going to be able to move in a region that is around that value. Let's see. Wrong one, sorry. P phi equal to Q R a phi. And how far it can move is going to be determined by the value of W. And these two curves are meant to represent constant psi curves that are going to bind the motion of the particle. And my particle in general in the RZ plane is going to be able to bounce around. So that's going to be something like this. It's going to bounce around, but it's not going to be able to escape that region of space for all the reasons that we discussed. Okay. No time to discuss this a lot longer. But in general, what we are saying is that there will be an oscillation in the R direction. The particle keeps bouncing back and forth while it's moving in the Z direction. And it's, again, bound by the curves where W is equal to psi. And the potential well can narrow if the magnetic field becomes stronger, and that will cause a bounce in the Z direction. That's a region that's also inaccessible to my particle. We are not going to have time to go into a lot of depth in here, but I hope this is enough to make you see that we are finding, again, the same result we already found for the motion of a charged particle in a non-constant magnetic field, that is a motion with reflection. Now, one more thing. We want to do is determine the motion in the phi direction. And I'm motion in phi direction. And that's given by the expression that we have for the canonical momentum. And well, I'm just going to write the solution. You know how to write this, so I'm not writing anything. We have it above. QRA phi divided by here, mr squared. Then phi dot changes sign when the numerator changes sign. P phi is a constant. In fact, we said that QRA phi equal constant is a magnetic, the trajectory in our RZ, well, in space of a magnetic field line. That means that this quantity changes sign when the particle crosses a magnetic field line. And if phi dot changes sign, that means I'm going to change direction. That means I'm going to have loops in the R phi plane. That's what's the picture in the textbook, which I'm now not going to reproduce, shows you're familiar with the cyclotron motion. This is what it is: cyclotron motion around a magnetic field line. And the motion is a little more complicated than a simple cyclotron motion in a straight field line, because the field line is not necessarily straight. The strength of the magnetic field is not necessarily constant, but it's essentially a harmonic motion if you're close to the bottom of the well, as I mentioned earlier. Now, the description of the motion becomes more complicated if the magnetic field is not time independent, but we're not going to get into that. What I would like to do in a very quick overview and reminder is remind you of what adiabatic invariants mean in classical mechanics, and how the concept of adiabatic invariant is not something that was invented in plasma physics, but it's something that we learn from classical mechanics. I am again going to follow how this is done in our textbook. This is a reminder. We know from classical mechanics that if a system is nearly periodic, that is, there is some periodicity that will be exact if the parameters of my system were time independent, but there is some time dependence on time scales that are much lower than the periodic motion, then the quantity J integral over cycle, it's the action integral of P times dq. Oops, lost a D. Trying to write quickly. This approximately constant. And this is the action integral. Now, this concept is pretty much imported as is in plasma physics. What I wanted to emphasize again is that we can learn a lot from what we already know from classical mechanics. The mathematical description is similar, and that's why I wanted to briefly mention this after we discussed the Hamiltonian method, because this comes from Hamiltonian mechanics, the action integral P and Q that are my generalized momentum and coordinate. So that's all I'm going to say about this part. And I'll let you read a little bit more in the textbook. Let's see, I'll decide if I want to put any of that in lecture 11, the 3 adiabatic invariants that we've not really discussed in detail. We'll discuss the first one. But these can be obtained from standard classical mechanics treatment using the periodicity of the motion in my system. And if you go check figure 3.24.24 in textbook, you'll see highlighted the periodicity in my system. The type of field or magnetic field we're looking at, mirror field, and each periodicity will give you an adiabatic invariant with different properties and different definitions, but you know how to write each one of them. You write them all in the same way. Okay, that's going to be it for today, and we'll see you back for lecture 11. Thank you.